Hey, this is Jon Kakaley. We're going to be solving the cocktail party problem with deep learning today in my project presentation. What we're going to be talking about today, quick overview of the cocktail party problem. You have a sound mix and you're going to separate it into its original sources. So I'll let you read the experiment goals and constraints at your own leisure. We'll get right into it. So what we're going to do, we're going to take this sound wave here. We're going to perform a short time Fourier transform on it. Now, a short time Fourier transform is like a Fourier transform, but imagine a small window that just scans through this sound wave, performing Fourier transforms as it goes, and the result of that is a spectrogram. Now, the reason why we want a spectrogram is because it shows us patterns better. It's 3 dimensions of data. You have the magnitude represented in color on a 2D plane. And look at this, in voice 1, you can see that the frequency peaks higher, and voice 2 doesn't have those peaks. So when you go down here, when they're mixed together, you can see the difference, and a computer AI network is going to be able to recognize those differences too. So it makes for training better. So once we create that spectrogram, we are going to create a soft mask. This is the matrix math for it, and all we're really doing is inverting the spectrogram. That's really all a soft mask is. So what you do is you take the mix of audio, you piecewise multiply it by the soft mask of the voice that you're trying to extract, and then the result of that is your separated voice. Then you just perform an inverse short time Fourier transform on this spectrogram, and you get a sound wave of the original voice that you're trying to separate. Now again, so how is an AI network going to detect this? Well, essentially what we're going to train it to do is we're going to train it to reconstruct an estimated soft mask. So we're going to do that with about 5 minutes of audio data of myself and a TV anchor. We're going to validate that training against an 8-second audio clip of myself. It's important that we normalize all of that audio data, in other words, smooth it, because AI networks can recognize patterns better in smoother data. We're also going to chop the spectrogram up into small chunks. Again, we do that because it allows for better pattern recognition. So this is the code for the AI network. This is the training results. It took about an hour to train it. And these are the results. Again, what we're doing here is we're inputting this sound into the AI network, and it spits out a reconstructed sound wave, completely blind to what the original sound waves were. We just have them here for comparison purposes. I want to focus on sample set 2 because it's one of my favorites, and look at how well it reconstructed this sound wave. It is very close to the original. I mean, you see some little errors here, like I think these little lines are longer there than here, and this little area isn't quite perfect, but it's pretty good. I measured the error. We're looking at about 3.5% error. I also want to go over to sample set 5 just to point out one area where it's not perfect. So again, this first chunk of the sound wave reconstructed nearly perfect, but this is supposed to be completely blank, and obviously that's not blank, so it pulled some sound data in from over there. But again, it recognized to some extent that it's supposed to be of a smaller amplitude because it did suppress the amplitude. So that is a good sign. It just needs to be made a little bit better. I also want to take a moment to play the sound for you.
Life is really simple, but we insist on making it complicated.
So that's my voice that was reconstructed in sample set 2. So as you can see, it's pretty good, but there's a little static involved, and that's what the error represents. So we processed 31 seconds of audio data in 14 seconds. So sound wave reconstruction in real time is definitely possible. You can also take away the deep learning is a highly effective method for this, average error of 3.4%. Now we need to get that error lower, because think about it. You listen to your favorite song, if it has an error of 3.4%, it's not going to sound good. So that's got to be improved. And once that's done, we can solve the cocktail party problem for an infinite amount of sources with future research. So here are my citations, and thank you very much.